Okay, now you are live. I don't know how many people will follow you through YouTube because it's better and much faster through Zoom, but still, it works. Now I have to mute this. Oh yeah, I didn't. Yeah, you didn't. Okay, looks great. So Jan, are you planning to put a UV in the NOIRLab acronym at some point?
Well, you can only go to U from the ground, right?
Well, I mean, but it's a lab, so.
Yeah.
Okay.
What time is it over there?
It's 5:04. Yeah, for you it's really early in the morning, right? So.
Oh, it's okay.
Sorry about that. Okay, so I think it's.
What time is it over there?
5:04. Yeah, for you it's really early in the morning, right? Sorry, that was me. Sorry about that. YouTube. Okay. Okay, now I can talk live. Okay, that's fine. I had two channels open and one was not mute in YouTube. Okay, now I see it. Okay. I think we can actually start. Probably there will be people joining in because I mean, I know more people actually show interest, so I'm sure they will be connecting. But I mean, since I'm sure many of you that are waiting, and of course the speaker is going to have many things to do, so we will start. Let me just give a bit introduction to your bio sketch, Janice. First of all, thank you very much again for agreeing to give this talk. It was really nice of you, especially given the time difference. So for those of you that doesn't know Janice, she did her PhD back in 2006. I'm sorry, I had to talk about dates back in. Well, it was at least it was the same century. You know, in my case, it was the previous century. So she did her PhD in University of Arizona in Tucson in 2006, if I remember correctly. And then she actually moved first to, I think it was NOAO, right, with a Hubble Fellowship, and then to Carnegie Observatories with a Carnegie postdoctoral fellowship. And then you went to a Space Telescope, right? I think it was 2011. From then, I think you took an associate professorship in IPAC, in Caltech, for a few years. And then less than 2 months ago, I believe, you have moved to the Gemini Observatory as a chief scientist, for the Gemini Observatory at the new NSF NOIRLab, although it's not new anymore. I think it has more than 2 or 3 years already, but still. So thank you very much again, and she's a well-recognized expert in the field of galaxy evolution, especially in the nearby universe, and also a good friend of mine. So please, Janice, go ahead, and thank you very much again.
Yeah.
If you have any other questions, just please, you could ask at the end of the talk. Thank you.
Okay. Can you see the cursor when I'm moving it, or no?
Let me see. Yeah, I can. Yeah, we can. Thank you.
Okay. Armando, thank you for the invitation. Do you remember this, Armando? The last trip that I took.
Well, actually, I wasn't there. I only had the
video this one.
With you. Oh, okay. Oh, yeah, that one, yes. The fun part, I do.
Yeah, the very, very last trip I took before the shutdown because of the pandemic was to Madrid. We had a PHANGS team meeting in the Observatorio, and of course caught up with, actually you can, here I am with Patricia, and then we had Gemara with Armando and Pablo. So hopefully I'll be able to see you all soon on another trip when things hopefully get better in the next few months and people begin to travel again. But I thought it was interesting that this is just a year ago, and the last time I saw colleagues around the world in person really was in Madrid. So the title of my talk is Linking Stars and Gas Throughout the Scales of Star Formation. And this will be a presentation of initial results from our PHANGS Hubble Space Telescope Treasury program. And the idea behind the program is to connect what I think of as the basic quanta of star formation, stellar associations, star clusters as resolved by HST. And we're doing this in a diversity of nearby galaxies, a diversity of galactic environments. We want to connect those with their birth clouds, the giant molecular clouds. And these are mapped, because you can read here, by ALMA. Before I get started, I'll give an introduction and talk about why it's important to link stars and gas throughout the so-called scales of star formation. And what does this even mean, right? The scales of star formation. You hear that a lot these days. Okay, so to get started, I want to link back to ultimately what the overarching question is. And of course, a major goal of astrophysics is to be able to answer this basic question, how do stars form from gas? And this is a simple question to pose, but still we don't have a full predictive theory of star formation. And the question is why? I mean, we've been doing this for many decades now. And the answer ultimately is because it's not as simple as studying giant molecular clouds on the sub-parsec scales to understand how, these clumps and protostellar cores and disks form from the molecular clouds and then turn into stars and the planets that orbit them. It's not just studying it on these fine scales, because when stars form, we know they don't form in isolation. It's been said a lot in the literature that most stars form in clusters or clustered environments. And of course, they don't just form in these clusters, but they have to form in the context of galaxies, which is, I think, what most of the folks online are interested in, galaxies and galaxy evolution. So star formation doesn't only convert gas into the stars and planetary systems, but the process depletes galaxies of gas. It also feeds back metals, energy, and momentum into the ISM. And that feedback might propel the energy, momentum, and gas into the halos of the galaxies, and even potentially beyond if it escapes the potential. So the simulation you're seeing here is from FIRE, feedback in realistic environments. And it's of a Milky Way mass galaxy. And what's being shown is how the gas responds to the feedback from massive stars, which originate on these small scales. And then how it has an effect, a cumulative effect on large scales. So this feedback, the star formation feedback, together with the galaxy scale inflows, the dynamics, it impacts the state of the gas and ultimately the future of star formation. And then the cycle continues. So what we've learned from these decades of observation across the full electromagnetic spectrum is that these mechanisms that drive, that regulate, that extinguish star formation in galaxies, they unfortunately conspire to operate over this vast range of stellar on parsec scales to interstellar to galactic to circumgalactic scales. And that's exactly what makes the problem extremely difficult. To make progress, we as astronomers, we've needed to divide ourselves into groups, studying all of these processes in detail separately. And oftentimes, this is out of necessity because specialized techniques are needed, to study the cold gas, for example, in the radio with ALMA, and then different galaxy samples, they're required to study each of these processes. And so this division and specialization, it's true on both the observational side and for theory, for the simulation work. And so to make progress and to bring all these things together and inform the development of a unified theory of star formation, we have to make systematic observations spanning all of these scales and all of these phases of the star formation cycle. We want to do it over a full range of galactic environments to see if there's dependence on the physical properties of the galaxies over slightly larger scales than the parsec scales over which stars are formed. And so this is where our PHANGS program is trying to take a step forward in the volume of the universe, where we can resolve those basic quanta of star formation, the stars, the clusters, and the giant molecular clouds. We're trying to take inventories of all these populations throughout the disks of many different galaxies and then use them to characterize star formation parameters. And I'll talk a little bit about that next. I'll start with an overview of the PHANGS-HST program, the greater PHANGS collaboration, and then talk about our specific science goals. So the color composite you see here was produced by the very talented Judy Schmidt, and it's based on our HST with C3 imaging of NGC 2835. This is the ESA Hubble Picture of the Week in September. These have been coming out fairly regularly over the past year, so you've probably caught a glimpse of the data we've taken over social media. So PHANGS-HST is a component of the greater PHANGS collaboration. PHANGS stands for the Physics at High Angular Resolution in Nearby Galaxies program. Our collaboration is an international group of over 70 scientists, and the goal is to systematically chart the evolutionary cycle between gas and stars in fundamental units of star formation through a diversity of galactic environments, as I've said a couple times before already. The overall effort, observational effort, is enabled by 3 large Treasury programs with ALMA, HST, and VLT MUSE. And with the ALMA CO 2:1 maps, we've obtained these for 74 galaxies, and this yields 1 arc-second resolution for the detection of giant molecular clouds. At the distances of our galaxies, that's down to about 80 parsecs, and with a sensitivity down to about 10 to the 5 solar masses. With HST, we're targeting a subset of 38 of these galaxies, and we're obtaining 5-band imaging from the near UV to the I of the disks of the galaxies, same areas that have been mapped by ALMA. We're also obtaining parallel V and I imaging of the halos. Now, of course, with HST, we have very high resolution. It's 0.04 arc-second pixel scale. And that provides a resolution of a few parsecs over the distances of our galaxies. And that enables us to detect young clusters and associations to about 5,000 solar masses. And with VLT MUSE, we obtain IFU mapping from 4,800 angstroms to 9,300 angstroms over the optical. And again, we're targeting all the same areas with ALMA, HST, and MUSE. This provides median resolution of about 0.7 arc seconds And the surface brightness limits, for those of you who are familiar with these kinds of units, are about a couple to the 10 to the minus 17th in CGS units in surface brightness. And that's in the H alpha line. We have been very fortunate to be awarded JWST Imaging for 19 of these galaxies in cycle 1, same ones with all three, the complement of all three observations from all three programs, and I'll talk about that a little bit at the end of the talk. So as an aside, here I mentioned that we're also getting these VNI parallels of the halos of the galaxy simultaneously with the imaging of the disk. And I just wanted to mention what we're doing with that because it actually provides good distances through the tip of the red giant branch. So this is the work carried out by graduate student Deep Anand from the University of Hawaii. He was an IPAC visiting graduate student fellow while I was staff there. Deep is doing his PhD thesis with Brent Tully. While he was at IPAC, he was working with me to do the photometry of the individual stars in the halo and to derive the distances based on the apparent brightnesses of the TRGB, which is, of course, a standard candle. And this is one example of a color magnitude diagram of the stars detected in the halo of this particular galaxy. And you can see that the tip is here, and you can then use the absolute magnitude of what the tip should be and calculate a distance of about 4.4 megaparsecs. And, this really comes for sort of free when you're observing the disks. So this has yielded TRGB distance to 11 galaxies so far, and then 5 of these are the first ones. 8 of these represent the best distances available in the literature. And of course, they're really important for our sample because in the nearby universe, of course, you can't use the redshift to compute the distances because the peculiar velocities move the galaxies all over the place and they're comparable to the recessional velocities. So can't do it that way necessarily. Now, going back to the 5-band HST imaging of the disk. This is a plot from the survey paper, and the point is that the exquisite resolution of HST allows us to identify these quanta of star formation. So multi-scale associations spanning over tens of parsecs, down to the most compact clusters with effective radii of just a few parsecs. Now, the structures in this star formation hierarchy are illustrated here for NGC 3351. And what I'm doing is to identify the multi-scale associations with a watershed technique, and these are overlaid in the blue contours on the ALMA imaging and the MUSE spectral map. This is the H alpha and N2 here. These expanded views at the top, they show the compact clusters and associations in white within the larger associations in the densest parts of the hierarchy. And the point is that these structures, they're not only important to study in their own right. There's a whole subfield of folks trying to understand the evolutionary processes of compact clusters and how they may or may not dissolve over time as a function of different parameters, physical parameters. But because these objects, they're effectively single-aged populations, you can use them as test particle clocks to time the overall star formation cycle. So you can imagine or can see that, you've got all these single-aged populations spread all over the galaxy. And here I'm showing a color diagram, U-B-V-I, with a simple stellar population track overlaid, and the colors of all these individual objects in gray overplotted. And this illustrates that the point that, they're clustered around this track. So yes, they can you can actually assign a well-defined age to them. And with thousands of these over individual galaxies, once you correlate them with the H2 regions in the molecular clouds, you can understand how long it takes for stellar populations to free themselves of the molecular clouds, for the feedback to clear the gas, and for example, molecular clouds to collapse or be in a state where they don't host any stellar populations. And that's what the HST data actually allow us to do with these associations and clusters. With the 5-band imaging, we do SED fitting and then derive the masses, the ages, and the reddenings. So now to the larger scales, the galactic scales, the overall parent samples have been selected to span the galaxy main sequence, as illustrated by the orange points in this plot of the star formation rate versus the stellar mass. And the galaxies that we're studying, they're relatively massive, about, they have masses about over 10 to the 10 solar masses, and they span a full range of spiral morphological types. And they have a variety of dynamical structures, such as bars and rings, as you see here. And here, these features are being illustrated by the ALMA CEO 2:1 imaging. The galaxies are at distances between 4 and 23 megaparsecs, and at declinations which make them ALMA observable. So all south of about dec of 20. They're not highly inclined to allow us to study stellar populations with HST. And of course, we choose ones that avoid the galactic plane. Now, the PHANGS-HST, I mean, there have been a number of HST surveys of nearby galaxies, and this study complements other major imaging surveys in this parameter space, such as LEGIS, which stayed closer to the Milky Way, out to about 11 megaparsecs, and spanned a large range of both dwarf and spiral galaxies. And the idea here is to not only study clusters, but to be able to resolve the individual stars, to reconstruct star formation histories from color magnitude diagrams. And so again, it spans down lower, but then it doesn't have as good of coverage of the spiral galaxies, which host most of the star formation in the present day universe. So you'd have to go out farther, a little bit farther in distance to get a fuller sample of that, which is what we do. And then on the other end of the star formation sequence are the starbursting galaxies and LIRGs, and these are the ones that are covered by the GOALS project. So in order to do that, they have to even go out farther to 100 megaparsecs. But here we're in a sweet spot where we have a significant sample of spiral galaxies, again, over about 10 to the 10 solar masses, where we can not only capture the disk efficiently with HST and ALMA, but then span this full width of the star formation sequence in terms of specific star formation rates. So things that are on the edge of normal with more activity to those that are approaching the green valley and shutting off their star formation. One of the things that has been a lot of fun about this project is that they've produced, the data from HST has produced spectacular images that the public is really interested in. So here you're seeing the 7 Hubble ESA pictures of the week that started about a year ago now. And our galaxies have also been featured in APOD, astronomy picture of the day, in 2 occasions. And also highlighted in the ESA Hubble calendar for this year. In terms of observational status, our program with HST started almost 2 years ago now. Actually, 2 years to this day, in fact, and we will be wrapping up observations in the next month. We only have one galaxy outstanding. As a so-called Treasury program with the Hubble Space Telescope, part of what we're doing is to release data products for the community, since the data can enable far more science than the areas that the team is focused on. So we did this, our first data release was at the beginning of the year. And in this release, we provided imaging products and visualization tools for 29 out of the 38 galaxies. And we will have future deliveries for the software that provides these censuses, these catalogs of stellar clusters and associations, including neural network models for cluster classification of the morphologies of these individual objects. We'll provide the full catalogs, and we'll also provide the products from ALMA and MUSE, so that you'll have a one-stop shop here. The other supporting data set, aside from ALMA and MUSE and HST, include ground-based H-alpha, VLA H1, and astrosat UV. And those will also become available in the next 6 to 12 months. And so we're hoping that this will provide the starting point for many other science investigations beyond just the ones on star clusters and timing the star formation cycle. And of course, a massive program like this it needs to be enabled by very large collaboration. Here you see the folks on the HST side of the PHANGS collaboration, our data working group, and just wanted to especially highlight folks who are junior scientists in our team and all applying for jobs this year. Here is Deepanand, which I pointed out earlier, was doing the TRGB distances, Kirsten Larson, Jordan Turner, and Sinan Deeger. He's a postdoc, he's still at Caltech. But Jordan, Kirsten, and Deep were all in the job market this year. And of course, our collaboration is part of the larger collaboration. I saw the picture on the first slide when we met in Madrid in person last year. And the only way this project goes forward is because we've brought together 3 distinct research networks. And these networks have specialized expertise on the radio observations, on the ALMA observations, and cold gas. We have another group who is focused on the spectral observations and understands the modeling of the nebular gas to make the best use of the VLT MUSE data. And of course, our group that I just highlighted, who are experts at space-based UV-optical IR imaging and resolved stellar populations. Okay, so I won't talk very much about that. It's just, this is the visualization of our overall pipeline that is producing these censuses of clusters and multi-scale associations. And the idea is that we're actually producing 2 types of catalogs. One of the challenges in studying resolved populations, star formation in galaxies, is that I mentioned that there's a star formation hierarchy, and it's a continuous hierarchy in the sense that it's very difficult to figure out how to segment the populations. So things that have been studied much more in the past are these compact star clusters. They have effective radii of about few parsecs. And they're interesting because the ones that are bound, at least a fraction of them, they're the precursors of globular clusters that we see and study in galaxies today. And so they're very long-lived. And again, there's a whole subfield studying these objects in particular. So they're the densest structures in the hierarchy. Even with the high resolution of HST, they're single peaked, they're barely resolved. at the distances of the PHANGS galaxies, but we can tell that they're clusters because they have slightly different profiles from an unresolved PSF. This is an internal note. It's not relevant here, but again, for these compact clusters in the catalogs will provide this aperture photometry and these physical parameters from the SED fitting, plus some classification of their morphology. What's been studied less in nearby galaxies, and there are fewer catalogs of these, are the associations that surround these very dense single peaks. But most of the star formation, in fact, are not concentrated in these very dense structures. The majority are in these looser associations. And so these are multi-peaked at the distances of the PHANGS galaxies. And again, we've created this separate pipeline, this separate technique to figure out the objects that are associated with each other, starting from the point sources. And then later on, I'll show that the technique is actually working in identifying things that have formed, at least we think, at the same time, so that they can again be used at these clocks. So again, these observations from the HST side, they started 2 years ago and will complete in the next month. And here is what the HSD imaging looks like overlaid with the ALMA CO 2:1 map. And it's just incredible that you see these very high resolution dust lanes in the HST imaging. And you see the ALMA imaging, the molecular clouds fill in the regions of these dust lanes. And the blue here are the youngest stellar populations in the near UV. And just visually, you can see how the stellar populations are clearing their gas. And that's actually why we see them, right? Because the feedback is creating these holes through which the light comes to us. But qualitatively, this is how we then use the data to understand what the timescales are for this emergence of the stellar populations from the clouds. Okay, so let me just move on a little bit faster here. This is just a zoom from the previous slide. I showed some of this before, but this is enlarged where you're seeing these compact clusters and the different kinds of morphologies from these single peaked, the most compact, densest regions to the multi-scale associations. And here's how they looked in the 5-band imaging. And here's another close-up with the ALMA of the locations of these clusters relative to the cold gas. So the main science goals, as I've alluded to already, are to place observational constraints on the star formation cycle. And of course, timescales are really important. We want to understand the onset of star formation in the clouds, the periods which the clouds are inactive, how long it takes to destroy the clouds, the overall cloud lifetimes, how long it takes to remove the gas from young star clusters, and the time when you see the H2 regions being cleared. With JWST, I'll talk about that at the end of the talk, we can then also provide constraints on the embedded phase when the gas is so dense around the young stellar populations that you don't see any of the light in the optical. So very heavily extincted, but the very, very first phases, and that gives us a time scale to the onset of star formation. We want to understand the relationship between the mass functions of the star clusters and associations.
Janice, sorry that I have to interrupt you, but there is a problem with the Zoom because I thought I had actually updated to the Pro version, but I did it not in UTC, but in standard time. Apparently, it's going to kick us out of this session. So I'm going to send right now another link. I'm really sorry for that. But it's telling me that it's going to shut down. So I want to let you know and the rest of the attendees before it happens. So just in 1 minute, you will get the new link. I'm trying to put it in the chat, but it's not doing it. So let me just really sorry about that. Let me just 1 sec, and I will send it to you, and you can continue. Really.
Okay, I'll disconnect now and reconnect.
Well, while you are okay, I think you are fine.